This is video help for problem 15.5. It's a short problem, but it has some interesting aspects to it. Object visibility has been defined as, the contrast to noise ratio times the square root of this n voxel. Remember, the contrast to noise ratio is just the difference between the signals that you get from two different tissue in a given measurement. And you're analyzing it. You don't know which one is coming from, but you're going to try to see if you can distinguish them. And divide by, I just assume a common noise. Remember, noise is sort of due to the electrons, and if the electron density is the same in these different tissue largely, then that's why we can say the noise is the same. So I'm looking at this contrast between two different tissues, A and B. And if I actually imagine not just doing a voxel signal, but say a collection of voxels, I kind of understand that I'll have, if I had n voxels covering my tissue A, and of course I'm getting a signal from A and B together really, and I'm trying to see if I can distinguish A, it's like n repeated measurements. You remember when I repeated a measurement n times statistically, I get a square root of n increase, remember? Signal goes like n, noise goes like square root of n. And so I get this increase in SNR, so you could kind of, this is a definition, but you can kind of motivate it then by thinking of this thing as, you're statistically adding up, some signals that you hope are giving you a good contrast. Well, if you take this formula and you say to yourself, okay, I'm going to, decrease delta x by 1/2, get worse resolution. In cases 6, 9, for example, in that table 15.1, that the signal to noise goes to what? Well, if that goes to what, then, you're assuming both of these do. Then there's some factor that this is reduced, actually. So what does this have to do to cancel it, to get the same visibility? So that's all that is. In general, I can say if delta x goes to 1/m delta x, and if the signal to noise then went like 1 over the square root of m, let's say, it depends upon what I'm doing with my other parameters, then the number of voxels has to go to, I've got to have m of these voxels covering A, the tissue A, to get the same visibility. It's just trivial, I got smaller resolution and then I got to get more of them together to cover a given distance. For part B, this is also just a qualitative discussion. The number of voxels here actually in a two-dimensional image is nx times some ny, some block of voxels. And that can be big with, say, both of them being big, a big square. But it also can be big even if one is small. I just have a few, say, vertically. I can have a long nx, say, to make up for ny being small. And you can argue then that you can see something if it's long and thin just as well as you can see something that's just simply, a big fat thing in both directions, but of course not as fat as this is long.